In this video, we're going to achieve what we were unable to do before, which is fully model the motion of a damped spring system. And we're going to use that with the tools of our complex numbers and complex exponentials. So first, the scenario. We have a mass attached to a spring and a damper, and you can think of this as like a door that you open up and it has a spring to close it, but there's also a little shock absorber built in, so it kind of moves more slowly or the oscillations don't go on forever. We've picked some particular values for the mass, the spring constant, and the damper. And remember, our goal is to predict the motion of the mass. So if we know just these ingredients, can we predict how this mass is going to move over time? And the answer at first is, well, no, not in detail. Then we think, well, we should be able to, because there's nothing in this physical system that we don't have quantified. If we can't predict what's happening here, we certainly can't predict big bridges and how they would move in the real world. So we certainly should be able to do this. In fact, we already have an intuition about what's going to happen if we move this mass, move it up, say, and then let it go. If we were to graph x against time, and we were to lift this up a little bit, that would give us an initial x. And then if we were to let it go, it'll move back down, then back up, back down, back up, with lower and lower amplitude. Other questions we want to be able to answer are, does it go like that curve, or does it go like this curve? Or does it go like this curve? Okay, we have the general parameters of what the motion should be like, but the details should all come from the quantitative information we have about the system. So let's see if we can use mathematics to get that quantitative answer. Notice the equation we're dealing with here is simply Newton's second law. Mass times acceleration is equal to the sum of the forces. As part of the solving process, we're going to move the spring force and the damping force over to the other side. And we see this quite lovely structure about the mass times the second derivative, damping constant times the first derivative, and a constant times the position value. And with the particular mass, spring constant, and damping constant, damping coefficient that we have in our problem, we get this differential equation. For all equations of this type, we're going to find there's a tremendously powerful approach, which is simply to assume that our x has some form. And our form is going to be e to the lambda t. That's it. Looking at this equation, our inspiration is that the position, whatever we choose for x, when I add it to its derivative and I add it to its second derivative, it all has to cancel out. It all has to equal 0. And an exponential is a pretty natural choice for that, because we know we're just going to get more exponentials as we differentiate. And so if we can gather them correctly, if we can group them, we should be able to get them all canceling out. That would not be the case, say, for t, or t squared, say. If we had t squared here, we'd have a t and a constant, and there's no way those could cancel out with constant coefficients in front to add up to 0. So the exponential is perhaps a surprising choice at first, but if we look at the structure of the equation we're working with, it's a very natural choice. It's one of the few natural choices we would have. That lambda is still unknown, though. We're going to be tracking it down, but for now it's just some number in the exponential, and imagine just different rates of decay, that kind of idea, being represented by different lambdas. Well, to have that be a solution, we have to be able to sub this x into this equation. We can do it here easily, but we also need x prime and x double prime. We need x prime, which is equal to, oh, another nice perk of exponentials, they have very simple derivatives. Lambda is a constant, so we take the chain rule derivative of this, gives us a lambda out front. And x double prime will be lambda squared e to the lambda t. Now we know what x is, and once we've defined what our x is, we also know what x prime and x double prime are. And so we can then sub into the differential equation, this thing here, and I'm going to put the x double primes and everything else in green. So we'll have lambda squared e to the lambda t plus 6 times x prime, which is lambda, e to the lambda t, and then we get 25 x's, and x is just e to the lambda t. There we go. X double prime, x prime, x. If we then factor that expression out, we notice a few, actually just one common theme. Every term has an e to the lambda t. And then we get a lambda squared. We have 6 lambdas left there. And here we simply have 25. And we need to solve this for lambda. And secondarily, this also has to be true for all t values. The one nice thing about this exponential, we've used this before, is that we can divide safely by it because e to the lambda t is never 0. Exponentials never equals 0. And that gets rid of that one, and dividing 0 by it doesn't change anything. So we get a wonderfully simple quadratic equation in lambda. Now, there's no nice obvious factors here, so what we're going to use is the quadratic formula. Lambda is equal to -6 plus or minus the square root of 6 squared minus 4 times 1 times 25 all over 2. And that tidies up to, this is -64 when we're done. So we'll have -6 over 2, -3. And we'll keep this in its current form for a second. Square root of 64 negative over 2 still. We can definitely work with this a bit more though, so let's do that. Keep going with our lambdas. So -3 plus or minus, I'll write it as 1/2. Square root of -64, well, that's the same as square root of 64 times the square root of -1. We can split off the -1 and there's our I value coming in. So we're going to have -3 plus or minus, there's an I here, and this is just 8. And so we get -3 plus or minus 4 i's. That's our lambdas there. Now remember where these lambdas came in. We assumed our solution was x equals e to the lambda t. Well, now we know the values of lambda that will satisfy this equation. And so we actually get 2 solutions out of this because there's a plus and minus option here. And they are simply e to the -3 plus 4i. And remember, is lambda times time. And x2 of t, which is equal to e to the -3 minus 4i times t. Now, 2 last stages. The problem right now is this is supposed to describe the motion, again, of this spring system up here. And if we look at this expression with complex numbers in it, what does it mean? We need to get back to reals. So this is complex, so it's true, but complex valued, which means it's hard to interpret. What we're going to do to get around that is we're going to first split this into 2 ingredients, e to the -3t times e to the 4t times I, and that's another way of writing exactly what we had. We're just recognizing that addition in the exponents can be split into a product. And likewise, that x2 of t is equal to e to the -3t times e to the -4t times I. So these guys are real already. E to the -3t is something you would have recognized before we added all this confusion about complex numbers in. These guys, though, the e to the 4ti and e to the -4ti, we saw through Euler's formula that we can combine these with Euler's formula. That's the exponential with an I, gives us sines and cosines, and appropriate constants by well-chosen appropriate multipliers. Again, this will be great after you've done, if you review this after you've done APSC 174 in your algebra, this is just going to be like, oh, of course. For now, we are going to wave our hands a little bit, though. And if we combine these 2 solutions, one of them is going to be an alternative. I'm going to call it x a of t, which is equal to our exponential. And by the time we combine these 2 complex exponentials, which are matched except for negatives, we can get a cos of 4t out. And likewise, a second solution that we could get is, again, e to the -3t, but for this one we combine the 2 complex building blocks that we have in a different way. We're going to get, no shock here, sine of 4t instead. And this is a major milestone because these are both all real. We don't have any complex numbers left. We needed them to get to here, but they are totally absent from our proposed solution, which is the prediction of motion of the spring. And also, these can describe, therefore, the motion of the spring and the mass. What do we mean by that? Well, let's take a look at the graphs of these two functions here. If we talk about xa, which was equal to e to the negative 3t cos of 4t, what that represents is an oscillating term, and the expression out front, think back to what you've seen before. If you put a multiplier out front, we often talked about that expanding or contracting the scale of the cosine. That's exactly the same thing here. It's the amplitude of that cosine, though it decreases with time. So the amplitude goes down over time. And what that looks like is this. Let's do it in green dashes here. I'm going to exaggerate the scale here. Cos graph starts at a peak, and I'm going to put up markers every 3 here. Is that right? That looks good. So cosine graphs, they're going down, then they go back, then they hit a minimum, then they start going back up. And what happens with this multiplier of e to the negative 3t is that the curve gets lower and lower amplitude over time. It's a peak, it's a 0, and goes back down. So this boundary here is defined by y, or actually x. These should all be x's, I apologize. X equals e to the negative 3t is this boundary curve, and the cosine graph just goes up to it and down to its inverted image, and back up to it again and down to its inverted image, and so on. You can test it out with Desmos or other software as well if you'd like to see it in more quantitative detail. But the key thing for us is that it captures exactly what we predicted back at the beginning. When we had this system and we looked at this, we said, well, we expect to see oscillations, and we expect to see those oscillations dying off with time. That is exactly what forms of e to the negative something times cos or sine are going to give us. In fact, the only other difference between that graph and this graph with the sine function is we're still going to have the negative exponential and its mirror image here. The function starts at 0 though, because sine starts at 0. If we plug in time values here and graphed it, we would get a peak around here, then it goes to 0, then it goes to the minimum, then it goes to another 0, and so on. The graph would look like this kind of damped oscillation with the amplitude getting smaller and smaller with time. That is a fantastic resting spot. Do take a look at that series of calculations, in particular the use of the assumption that we built in that our x value was equal to a simple exponential, and how it led us through complex numbers and Euler's formula to exactly the kind of prediction qualitatively we expected, damped oscillations. How do we use the two solutions though? Well, what we end up bringing to bear now is some initial conditions. Imagine we have this mass system, and we're told some properties of the system when we start it before we let it go. And all we mean by that is if x of 0 equals 4, what we're doing is we're lifting the mass to x equals 4. If we have x prime of 0 equals 0, the mass starts with 0 velocity. X prime of 0 is just the velocity term. And so what we're describing here is that we're going to lift the mass to x equals 4, hold it steady, just so it stops moving, and then we let it go. So we're going to lift this up, hold it for a second so it's not moving, and then boom, let it oscillate afterwards. From that, we should be able to produce a much more quantitative prediction about the graph and the motion. And what that's going to entail is finding the full solution that satisfies what we call these initial conditions. Initially, it has height 4 and velocity 0. All right, so what we get out of our earlier work is that we had two building blocks, the e to the negative 3t cos, e to the negative 3t sine 4t, and so the general solution, every possible behavior of this system Again, this will make tons more sense after linear algebra. After linear algebra, I'll just be like, of course that's what it is. There's a subspace of solutions that is defined by linear combinations, blah, blah, blah. Anyway, some number times e to the negative 3t cos 4t plus some other number e to the negative 3t sine 4t. So this is a constant times our a solution, and then another constant times our xb solution. No matter what you do at the start with the motion of this spring, it is going to be made up of the motion, the prediction of the motion of this mass is going to be made up as a combination of these two expressions here. And now our goal is to use x of 0 equals 4, x prime of 0 equals 0 to find a and b. That's it. This part here, there's no real calculus going on. There's no real physics going on. It's just taking this general form and saying, well, if I plug in 0 to this, I should get 4. If I plug in 0 to its derivative, okay, a little bit of calculus. Plug in 0 into the derivative of this, I should get 0. So we're just going to set up some equations and solve. Let's do that first condition. T equals 0, x equals 4. So this whole thing is going to be where we sub in t. Do this in color. So the 4 value is what we get for our position. And it should be a e to the 0 cos of 0, because time is 0. And then b times e to the 0 sine of 0. I'll just put the zeros in afterwards like so. So to have our mathematical solution start at x equals 4, at a displacement here 4 at time 0, this equation has to be satisfied. This equation has cos of 0, which is 1. This whole thing ends up being 0 because sine of 0 is 0. And so we get one nice freebie here. A equals 4. Lovely. Now for the next term, having the derivative equal to 0, we're going to have to take the derivative of this. And I'm not going to lie, this gets a little messy just because of the product rule and everything else. So I'm just going to copy this over to the next page, and we will work with that there. All right, I'm going to leave the a as an a rather than the 4 value we just found, just so we can kind of see a general pattern emerging here. And we'll be able to plug in the known value later. So first off, we get the derivative of the first term, which is a product rule. So I'll have negative 3 e to the negative 3t cos of 4t plus the exponential times the derivative of the cos, which is negative 4 sine of 4t, plus, for the b term, we're going to have b basically the same pattern, though just a reversal of the sines and cosines, and then plus e to the negative 3t, derivative sign is positive cos, so we'll have the 4 and cos 4t. So again, these 4s are just coming from the chain rule from the sine and cos. These negative 3s are coming from the derivative of the exponential's exponent. Then we sub in our x prime of 0 equals 0, and that means we're subbing in t equals 0 everywhere here. So again, we're going to have our velocity 0, okay. Then we're going to have a times negative 3 e to the 0 cos of 0. I'm going to put the zeros in a second. Minus 4 sine of 0, just to highlight where they all are. That was a 0 there. And so that is our first term expanded with the zeros in. So we're going to have our b values, same pattern, e to the 0 sine of 0 plus e to the 0 times positive 4 times cos of 0. Just putting all the zeros in green to highlight that they were where the t's occurred in the previous line. Perfect. Now we can do some cancellations. Again, the sine of 0 is 0, so we can wipe those terms out completely. Sine of 0 just multiplies everything away. The cos of 0, of course, is equal to 1. And that cos of 0 equals 1. And e to the 0 is 1. So what we end up with next is 0 equals minus 3a, that's it, plus 4b's. And here we can use our earlier fact that a was equal to 4. I'm going to bring that to the other side. So we're going to bring it positive 3 because we moved it times 4 equals 4b. And so cancel the 4's. We get b is equal to 3. And so our solution is x of t equals this expression up here. That was our solution. Now with the value of a being 4, negative 3t cos, and 3 e to the negative 3t sine. This function, guaranteed, satisfies these initial conditions because we set up the equations for those coefficients 4 and 3 to achieve that goal. You can now use Desmos or some other graphing tool to generate a graph of this and see that it satisfies both those initial conditions and looks like these kinds of graphs here where we have the oscillations dying over time and there's still oscillations going on though because we have the spring mass system being driven the way it is. So, full analysis of a spring mass system complete there.